Hi, and welcome to TME Presents webinar, Designing for Energy Security in an Unsecure World. My name is Nicole Matthews, and I'll be available to assist with most technical issues that may arise. If you have trouble connecting, you can email me at nmatthews@same.org, or you can send me a message through the Q&A box located at the bottom right side of your monitor. Lastly, you can also call WebEx at 1-866-779-3239. During the presentation, please submit all your questions for our speaker through the Q&A box. Finally, this webinar is being recorded. A link to the recording will be made available to all attendees within 3 business days. Thank you for your participation, and I'll now hand it over to our moderator, Chris Halpin.
Hello, everyone. On behalf of the Society of American Military Engineers, I would like to welcome you to the webinar, TME Presents, Designing for Energy Security. I'm Chris Halpin, President of Celtic Energy, Inc., and I'll be your host for today's webinar. I also serve on the SAME Energy and Sustainability Committee. So the TME presents From Print to PDHs. You've read the article, now learn the rest of the story. Take a deeper look into articles featured in the Military Engineer through TME Presents Professional Development Webinars. This is the first webinar of the TME Presents series. We hope you like the idea. Since 1920, the Military Engineer has been the leading voice chronicling the accomplishments, the contributions, and the legacy of military engineers and those aligned with ensuring the national security of the United States. Through TME Presents, professionals from industry and government will get in-depth insights into projects, programs, case studies, and new technologies covered in the Military Engineer. Webinars will go beyond what's published in the magazine, detailing lessons learned, challenges and failures, and most importantly, solutions. In an effort to engage industry members of SAME, we have planned this webinar, Designing for Energy Security. We hope that the information presented will be useful in determining the level of energy security at your individual sites. Following the webinar, the presentation will be emailed to all attendees within 3 business days. Watch out for a follow-up email containing the presentation, PDH certificate, and a link to a recording of this webinar. This webinar would not be possible without our presenter, so I'd like to sincerely thank Rob McAtee for his participation. I would also like to thank each of you for joining us today. I'm looking forward to the presentation and to your questions afterward. I encourage each of you to send in your questions as they arise. You can type questions in the WebEx Q&A chat box and submit to all panelists. We will answer as many questions as time allows during this live webinar. After this webinar, you'll be automatically routed to a survey page. Please participate in the short post-event survey so that we can address any concerns for future webinars. I would like to now introduce our speaker. Rob McAtee is founder and director of Mason & Hanger's Energy and Sustainability Services Department, a special entity within the company dedicated to increasing facility performance, improving energy productivity, and promoting sustainability. Prior to his current role, Rob was the director of mechanical engineering at the firm, where he was responsible for the performance of a large department designing HVAC, plumbing, fuel, and cogeneration systems with an emphasis on high performance and mission-critical facilities. He began his career with Siemens Power Corporation and a group dedicated to improving the safety of nuclear power plants in the U.S. and Europe. Rob holds a degree in mechanical engineering from the University of Virginia. He's a registered professional engineer, certified energy manager, and lead accredited professional in building design and construction. Without further ado, I'll pass the call over to Rob.
Great. All right, thank you, Chris, and thank you, Nicole, and thanks for everybody for joining in today to talk about energy security. So we will dive right in and cover a lot of the ground, not only designing for energy security, but sort of trying to set the stage on why that's so important and why we're hearing so much about it today and over the last couple years. So there are a variety of reasons to care about energy security, and we'll talk about a few of them. Probably the least important is economic, but it's important nonetheless. This first slide provides a couple graphs, just kind of giving some snapshots showing the economic loss associated with loss of power. And for much of this discussion, I'm going to be focusing around military installations or federal installations. Even in federal installations and especially military bases, there's of course disruption to mission, which is critical, but the bases are pretty big, and there's an awful lot of economic activity that goes along with their operations. This first chart is from a report that that was put out a few months ago by Noblus that has some good information, and it shows sort of a middle of the road value of the loss associated with various durations of outages. So if you just take a 5 megawatt load, which would be fairly small for an installation, and assume it's going to have a 4-hour loss of power or 4-hour outage, that would result in close to $400,000 in economic loss. So that's pretty significant right there. The bottom of the screen shows the losses, economic losses that we see in the data center world. Average outage of $740,000 for last year. It's pretty significant. As I said, that's probably the least important reason to be pursuing energy security. Emergency response is vitally important. If there's ever a catastrophic event, be it weather or otherwise, these are the people that I would want looking out for me and my family, and they absolutely need continuity of operations, and they need to be able to do what they do, stage their operations, and so it's vitally important that U.S. facilities, U.S. military bases can stay up and running. And of course, then there's the mission, sort of the overseas kind of force projection or scientific endeavors, whatever it is we're doing, you know, throughout the world. You know, it's a global digital enterprise now. Rapid connections to data centers all over the world, multiple satellites, uplinks and downlinks. Every step in the chain needs to have power and energy security that includes cooling, or we're not going to be able to do what we need to do, and that could have some very severe consequences. So I don't need to spend a whole lot of time on that, just to make the case that energy is important. Pivoting on from that, you know, why are we talking about securing the energy? Well, you know, there's some cold hard facts that we have to face up to, and there are some threats to energy security from a variety of causes, but it is safe to say that the number of outages, if we're talking just about electricity, has been increasing over the past decade or so, and there are a variety of sources that point to this increase accelerating. My firm does an awful lot of work overseas, and of course the U.S. military and other agencies also operate overseas, and I think we all know that we enjoy relatively good power compared to the rest of the world. Before I talk about that more, I'll also focus on this lower slide, or this lower image on this particular slide, showing the outages at U.S. military bases over I guess a 3-year period, just a couple of years ago, where there was some pretty good data. And you know, this is real data. There are hundreds of outages experienced at our military base. A lot of them are relatively short and not so disruptive, but many of them are several hours long, and can and have provided significant disruption. But as I said, we're lucky. We have good power. The dark areas are countries that enjoy very reliable power. Even so, our grid in the United States you know, maybe 99.9 or even 0.99% reliable, but that still leads to a number of hours where we're likely to have outages. But for the rest of the country, including especially Africa, there's a real gap in energy security. So if we're doing missions over there or building operations over there, we really have to work extra hard. I thought this would be a good time to throw out a couple definitions just to make sure everybody's kind of thinking the same thing when we talk about energy security. The concept, I think, is fairly easy to get your head around, but there's a couple maybe little nuances to it in the DoD world. So, you know, sort of from the very top level, the United States Code, energy security is about having access to reliable energy and to be able to complete mission essential requirements. Lately, there has been some additional guidance, including an Army directive related to storage, but the Army's Office of Energy Infrastructure has sort of further designed energy security and resiliency as having generating assets, storage, and they're going all the way to microgrid control system. So the control system is a very important part of that. So we'll talk a little bit about, you know, the key components to energy security a little later in the presentation, and just one last point to make clear, especially for folks that may have had a lot of experience working on critical operations power systems that you might see in data centers or municipalities, specialty facilities that can't have even, you know, outage for a second. That's sort of a subset of what we're talking about. It's of course vitally important that our you know, mission critical buildings don't have power, but we handle that in a little different way. The broader topic of energy security is really about keeping, you know, the operations going from a larger perspective. So this would be sort of multiple buildings so that we can complete the mission. So as I said, there's a lot of concern about this, a lot more in the press about this, and for good reason. There are some things that we have to look out for and address. So certainly, you know, they range from weather to nefarious activity. But we'll start with weather. I love this particular slide. I'm sure the insurance companies hate it, but it addresses the number or displays the number of billion-dollar weather events. Doesn't matter whether it's a $1 billion event or an $80 billion event, but just the sheer number that are occurring per year, and it is normalized to, I think, 2016 dollars. So it's not just that things are getting more expensive. These are the number of events that, you know, required monetary payouts. And it's pretty striking to me. I think it demonstrates a pretty clear trend upwards in terms of these events increasing. A couple points that I also took away from it. One, the hurricanes aren't necessarily the big players in this. Those are the yellow columns, certainly a component, but not the biggest component. The biggest component is just plain old severe storms, thunderstorms that produce straight line wind, hail, and spawn tornadoes. Those have really increased in their damaging effects. Also, flooding seems to be on the rise. No pun intended, but there does seem to be more damage associated with flooding. Now, you know, we don't have to talk too long about what might be causing that, but you know, there is a lot of talk that just having more energy in the atmosphere is going to increase the severity of storms. But we don't have to just worry about weather. There are plenty of other threats out there, and a lot of them just involve other agents or individuals. So these are just a few headlines we've seen in just the past couple of years. Our infrastructure is vulnerable to physical attack, and of course there's a political angle to energy security, where neighboring states can affect each other's energy security simply by turning off valves or shutting off power feeds. And as we saw in Puerto Rico last year, aging infrastructure or fire can do an incredible amount of disruption if it happens in the wrong place. Here's a big one, though, infrastructure. Just touched on that a little bit. We're in a lot of ways a victim of our own success, particularly in this country, in that our grid has been so reliable for so long. We kind of just set it aside and really haven't spent the time or money that we should have in maintaining it. As a result, we've got a pretty lackluster report card from the American Society of Civil Engineers, something close to a $200 billion deferred maintenance backlog. And that's a problem, and something that we do need to address, and we need to do it smartly, but we do need to address, because it's going to start affecting us. In fact, it already is. This example, hopefully you can see this image here. I had it a few slides back. This was a San Bruno gas explosion that I think happened 7 or 8 years ago in California. Is absolutely an example of what happens when the infrastructure begins to degrade. This was a 30-inch gas pipeline that had been in the ground for over 50 years. And I believe the utility tried to increase the gas pressure to keep up with demand, and the pipe just couldn't take it. And I believe 8 people were killed in this particular explosion. So it's an example of what happens when we don't keep up with infrastructure. This other image is supposed to represent an old transformer at a substation. Sadly, that is the case. A lot of the transformers at substations are quite old and past their, what would normally be considered their useful life. And the reason that's a problem is because these are not off-the-shelf products. If they go bad, and occasionally they do, it takes quite a while to get replacements for them. So what often gets held up as the biggest threat, and especially in the defense-related communities, I think for good reason, cybersecurity is brought up as one of the biggest drivers for really addressing energy security and really making sure that our installations can withstand a loss of grid power. The U.S. electric grid is a marvel. It's I've heard it called the biggest machine in the world. I believe it. It's completely interconnected, and you can see from this top image that we have tens or thousands of miles, maybe even tens of thousands of miles of high transmission power lines. They're all interconnected. They're all controlled by industrial control systems, varying levels of sophistication and ages. Similarly, on the natural gas side, we have thousands of miles of gas distribution pipelines, and you can see from this image, every one of these dots represents a compressor station because the gas obviously needs to be pressurized and pushed along these pipelines. Well, there are also industrial controls associated with that, and of course they're very much interconnected now. Much of our power is now produced with natural gas, and of course you need electricity to drive all these compressor stations. So they're interrelated, and they're both vulnerable to a degree of on cyber attack or you know, any kind of failure in these control components. And the outages generally, if they happen on a big enough scale, will begin to cascade, as we saw in 2003 and other years with these big outages. Once you take down a big enough block, generally systems are in place to, generally that tends to take out other areas, and it can take quite a while to get those systems restored. So cybersecurity, it's not a question of if it will happen or even when it will happen. There are active attempts to hack into and do bad things to our energy infrastructure. They are being tracked and reported to the extent that they can be tracked. And of course, we've seen in Ukraine just a little over a year ago. Well, actually, it was less than a year ago. It was December. They were taken down. A large portion of their grid was taken down. It was absolutely clear it was a cyber attack. You can say who you want, you know, did it, but it was a well-coordinated cyber attack. They got into their systems. They cut off breakers. They cut communications between various substations and utility operators so that they couldn't see what was going on. And then they erased a lot of their hard drives for good measure. So it's sort of a multi-pronged cyber attack, and that's exactly the kind of thing that has got folks worked up for good reason. It's a vulnerability in our power network as well, and so that's why we're talking about energy security and talking about improving it. So what can we do to improve energy security? So we're going to kind of round out this whole presentation, you know, sort of as a spoiler alert, going to be talking about, you know, the long ball, the ultimate, which is sort of the microgrid solution that I'm sure a lot of you have been hearing about, distributed generation and combined heat and power, and we'll define all those in just a little bit. But there are a few things that you can do just to improve energy security along the way with new and existing projects, and even before we do that, it's important to sort of set the framework for what you need to address to really achieve energy security. So these are the key components as we see them for energy security. You kind of need all of these, or you're not going to be able to maintain operations for very long. Of course, you need generation. You need a way to store energy. Most often, that's in the form of diesel fuel, but it doesn't have to be. You need to get the energy to where it needs to go, and you need to be able to control the energy. So we're going to jump in. I'm going to jump into each one of these. So we'll start with generation. I think this is the easiest for everybody to get their head around. Some way, most typically a reciprocating generator, and most often burning diesel fuel, but that's the most common. But there are some other ways to make electricity and power. I will stress this several times. This is huge, and not just because I'm an energy guy. Efficiency is every bit as good. In fact, is better than generation. Every watt that you can save is a watt that you don't have to generate, and arguably, is, you know, makes you more secure overall. So when we are designing facilities, it might not be as sexy as a microgrid to talk about, you know, good chiller plants and good building insulation and good glazing and good lights, but it's every bit as important. So continuing on with generation, we can sort of talk about, you know, the business as usual approach, and then go through sort of the better improvements or betterments on that business as usual approach. Most facilities are powered, at least in the U.S., are hooked up to a municipal or a utility grid. which is generally good, but again, it's not always 100% reliable. So in terms of energy security, it would not be considered secure. There are too many links in the chain between where the electrons are generated to an installation. So the business as usual approach has been building by building backup power. That's absolutely better than nothing and has served us pretty well over the decades, but it's expensive. Often the generators aren't maintained the way they're supposed to be, so you think you've got backup power and you really don't. It's relatively inefficient. So there's some real problems with building by building backup power, and one of the ones, actually one more problem that we're seeing more often that is surprising us in this heavily networked age is it's getting more difficult to draw a box around your critical facilities. And by that I mean you may have a command and control facility and it's sort of a no-brainer that needs to be backed up, but you might not realize that there's a data switch somewhere that's serving that particular facility, or there's some other interconnection that you haven't thought about to 2 or 3 buildings over, or another building on your base that isn't backed up. So I just want to make that point that the building by building generators are okay, but we need to do better than that. So the next step would be to put in place a simple microgrid. We'll talk a little bit more about that, but just a way to island your base or your compound from the broader grid. So this would be sort of, it doesn't necessarily need to be a standalone generator plant like you see here, or a consolidated plant. You could somehow control multiple generators in different areas. This is a little more common, but the concept is you're getting all your generating assets kind of synced up and islanding your installation or facility from a broader grid. Again, it's good, but not terribly efficient because you're relying on diesel generators. And further, you've got kind of these assets, these very expensive generators that need to be maintained, and you're really not using them all that often. So taking it a step further, if you can get a more advanced microgrid with a little better controls and integrate other sources of renewable energy, as well as take advantage of combined heat and power, then you sort of got the win-win-win. It is expensive up front, but it has multiple benefits. As I said, cleaner is better. I think I probably hit on a lot of these points here. Combined heat and power basically takes advantage of the waste heat that's produced when power is generated, especially from fossil fuels. Typically only about 30% of the energy that comes from the fuel actually ends up getting converted into electricity at the point of use. So the remaining 70% is just in the form of heat. If you can generate that power closer to where it's needed, and you can find a use for that heat, such as heating your buildings or driving processes, you will almost always be much more efficient. One more thing on generation. If you've got a high threat facility, and more installations are being considered, high threat, even stateside, you really need to protect your generation and your fuel, but especially your generators. And that can be a little difficult to do sometimes because generators need a lot of air. They need air for combustion. They typically need a lot of air for cooling. And so in order to get that much air moving to them, you have to typically have very large air openings, which presents a problem if you want to secure those generators. So you typically have to protect your openings. The biggest openings need to be protected by louvers, hardened louvers. You can do that if you're doing just a single building. There are some pretty cool modular products that we've used, like this one in the lower left corner here. It's sort of a generator in a pod. You just set it down and plug it in. It's pretty cool. It tends to be pretty expensive. If you consolidate, if you've got a bigger operation, then you can consolidate your generating assets into some hardened construction, but you still need these louvers. The louvers are rated. A lot of security measures are rated in terms of time, 15 minutes or 60 minutes, and this is pretty much the definition of it. It's just guys going at it with tools and guns and whatever else. How long does it take them to break through it? Nothing's going to last forever, but 60 minutes is a good long time. Hopefully, if people are attacking, you can get some backup in that amount of time. It's also a good indication that a lot of people's jobs are more fun than mine on some days. But it's real important to think about protecting the equipment that you're putting into your base or operation to provide energy security, because it's not very secure if someone can just take it out with a firearm or a sledgehammer. So the next piece of the puzzle is storage. As I said, by far the most common kind of storage is diesel storage, on-site diesel storage. Again, efficiency is huge. The less you need to maintain your operations, the more efficient your operations are, the less storage you're going to need. And storage is also quite expensive. So it's really important to consider efficiency in this equation. A couple points on that, a couple really important points. First, natural gas doesn't typically count as storage if it's coming from a utility off-site. Now, you can store natural gas, and we've done it. You can compress natural gas on-site, but you need to protect those big storage vessels. But unless you're doing that, if you're relying on an outside utility for your natural gas, it may even be more reliable than grid electricity, since trees aren't falling on your pipes usually. It's still not considered secure, because if there's a major event, it's likely that you're going to lose that gas feed. Needs to be maintained. We'll talk about that, and we'll touch a little bit more on batteries. But batteries are really in the process of changing a lot of things. They're still expensive, but that's changing. And so while every job isn't going to get batteries in the near future, we need to at least be thinking about them and talking about how they will be integrated, because ultimately they will be. So back to diesel fuel, because I said that's by far the most prevalent means of storage. It's really, really important that we all realize that diesel fuel has a very short life. You can't just fill a belly tank in a generator and let it go for 3 years and think that that generator is going to run right when you need it. There's an amazing array of microbes that grow in diesel fuel. Diesel fuel absorbs water and a whole lot of other contaminants. So filtering the fuel, additives in the fuel are incredibly important. Collectively, that's called fuel polishing. And it can be time consuming, especially if you're at a larger facility where you may have 100 generators. Between exercising the generators and making the rounds to clean the fuel, filter the fuel, that can eat up a lot of time and expense. Also, the tanks, just like the generators, the tanks need to be hardened or hidden. The low-grade tanks are great, kind of gets them out of the way, so long as the geology is suitable for that. If they need to be above ground, then they need to be either behind hardened construction, or the tanks themselves need to be fire rated and also ballistic rated if you're in a high threat area. Oh, and one last point. Fuel deliveries. We do a lot. My firm does a lot with overseas locations, but it's probably, it is certainly a good idea to kind of think about what you're going to do in your, in your refueling state. You're talking multi-day outages or multi-week outages. Worst case, you're going to need to make arrangements to have new fuel brought in. And you need to think about, things like turning radiuses for the truck, where the truck is going to offload the fuel, remote filling, and all of that stuff. You don't want a big bomb driving onto your base. What potentially could be a big bomb driving onto your base. One last thing is storage. Renewable energy is, you can call it the new form of storage. It's not going to take the place of fuel, at least not yet, but and it's not going to take the place of most generation, because we're talking about PV or solar, or sorry, PV or wind. You can't always, at any given instance, you can't assume that you're going to have a whole lot of output from the renewables, because the wind might not be blowing or it might be night. However, over the course of a multi-day outage, you can be pretty sure that you're going to be producing energy from these systems, and what that's going to do is take the load off your generators, and that's going to save you fuel. So that could maybe be used to reduce the first cost of your fuel storage, but more typically what it gives you is just longer runtime. You get all the other benefits of renewable energy, but you also can extend your mission, and that's what this this bar chart here shows for a variety of for 3 different locations in the U.S. This would be with 5 megawatts of PV. So this is a big installation backing up a big installation. But you're getting a day or more of continued operations on top of all the other benefits of the renewable energy. So distribution, just quickly, trees are public enemy number 1. The vast majority of power outages aren't the result of a large power plant going down, and typically aren't even the result of transmission lines going down, although that does happen. It's typically, an ice storm or windstorm taking down some trees or a substation fairly close to the activity, and so. Or even inside a base, you can have individual buildings go down just from a stray palm leaf. So you really need to think about trees, especially if you're inside the fence line. Have good practice there. And then when you're siting transformers, or at least when you're thinking about energy security and doing these assessments, you need to think about where they are and protecting them as well, even from, it doesn't have to be a terrorist attack to have somebody take out a lot of activity of, a transformer's sitting near a corner where somebody can just do something boneheaded and run right into a transformer. So that's the distribution side. Finally, controls. This is hugely important, but you need to make sure everything's working together, and it also, of course, touches on cybersecurity. So there are multiple control systems in any facility, any military installation. Dozens of different kinds of control systems, from fire alarms to security to building automation systems for HVAC, and of course for electrical controls, for power controls and generator paralleling. Monitoring is important for so many reasons, but you really need visibility in your operations to see what's going on. And so I'd kind of throw out there that it's one of the very first things you can and should do is to give yourself visibility into how your individual buildings are operating. You'll be able to know, is a particular building off? Did a palm frond just short out this particular building? So you don't have to wait for people to start calling you, but you'll also be able to address that critical thing I was talking about earlier, the energy efficiency thing. So many buildings still in the U.S., in particular on military installations, do not have effective power metering. And so just being able to get more power metering to show what the buildings are using will go a long way in reducing the overall energy usage. Last thing on controls before we get move off of it. Commissioning, vitally important. Another relatively low-cost thing that we can do. Again, it saves energy, so it improves energy security and it improves overall performance, especially if you're talking about any sort of power system. Anything we're talking about later in this presentation related to microgrids, sophisticated power control equipment, it has to be commissioned, and then it has to be recommissioned every few years. All of this stuff will kind of drift. That's true of any system, so it's not just that power systems are notoriously bad. Commissioning is vitally important because controls, again, we're really worried about cybersecurity. A whole big part of this whole topic of energy security, as I've been pointing out, is related to cybersecurity. There's a lot of worry that the utilities, the outside utilities, are going to get hit. That's going to bring down the network, and so we want to make sure our bases are, it's going to bring down the grid. We want to make sure our bases are protected. The last thing in the world we want to do is put equipment and systems that are designed to protect our energy security that are vulnerable to the same sort of cyber attacks. So when we're designing systems, any kind of system, but especially these power systems, we need to really take cybersecurity into mind and take it seriously and apply what's called the risk management framework to the systems. This has been adopted by the latest UFC, which was put out last fall, and I think it's been updated once. You need to make sure that you're thinking about all the areas of operation, and it's not just IT type stuff. There's your control components, and there's also a physical security in terms of access to computer workstations and security. It's a big topic. It's a lot more than what I can talk about here, but I think it's important that everybody start thinking about the risk management framework. As I said, there's a unified facilities criteria. It is UFC 4-010-06. Not horribly long, but it's pretty dense, and it takes a little while to get your head around. It is derived from NIST standard 800 guide, and there's a pretty good guide that I would recommend as maybe the first step, even before you get into this UFC. This special publication 800-82, it's a little bit longer, but at least to me, it's a little more accessible and does a little better, or it's a great introduction to this standard. But again, it's all about this risk management framework. So what I've covered so far is just sort of outlining, why energy security is important, which was fairly easy to do, and what are some of the threats to energy security, and then went into some of the key pillars and hopefully hit on a few things that installations can do before we go all the way to the distributed generation and microgrid approach. There's something called an energy security assessment that I think is vitally important. That's also a critical step in achieving energy security. And in other words, before you go and think that you need a shiny new cogen plant with microgrid capabilities, which you may, but before you do that, you really need to see what you've got and see what your vulnerabilities are, because at the end of the day, there's going to need to be some prioritization of individual bases and indeed individual buildings within the bases. So that's where the energy security assessment comes in. there's some pretty good guidance out there. It's actually, there are different names for this assessment, but you know, this is pretty pretty clear in terms of what it is. You just need to go out, have a kind of a holistic view of your entire installation, see what are your critical buildings, see what you've currently got by way of backup power systems, how interconnected they are, and then begin assessing your threats and vulnerabilities. There's a sort of a probability associated with each of the threats that gets cranked in. Yes, you could be hit by an asteroid, and I guess that's probably an even probability, but it's a relatively low probability compared to maybe a site in Florida that is susceptible to hurricanes. So you come up with the array of threats, translate those to vulnerabilities, and then most importantly, you begin to address the threats. And you'll probably have to start slowly, but there will, arising from this kind of assessment, there will be some simple things you can do right away, and such as, like I said, trimming trees or making control improvements, or maybe just improving redundancy of power or increased fuel storage. Those would all be kind of relatively simple measures that you could do before you went into the more complex measures. This is more or less a requirement, but it's been such a big requirement that it's only been it's been fairly recently where the agencies, at least from our perspective, have really been embracing this and trying to figure out how to apply this. Just one more thing on these energy security assessments. I could almost do a whole presentation on this, and I don't need to do that. It is a sort of a step-by-step methodical process just to see how it is you're doing. When you decide to go down this road, it's really important that you get buy-in from the key stakeholders. You can't do this, or you can't do it effectively if the command structure isn't on board with what you're doing, or you can't do it effectively if the command structure isn't on board, but the facility level and the maintenance level staff doesn't understand what you're doing and isn't really supporting you in this process. It really takes everybody understanding what's there, and it's really a collaborative process. So hopefully what comes out of an energy security assessment is you'll find a number. You'll certainly find a number of vulnerabilities, maybe some threats and vulnerabilities, and different ways to address them. All of them, almost all of them, are going to cost money and are going to require some action. And so what you may find, and what a lot of installations are finding, that on a sort of a per kilowatt of backed up energy, things become, at least conceptually, easier at a bigger level. So that's where this quote comes in. If it's difficult to back up just a few buildings and make that work, maybe it's a little easier to back up a whole installation, and that's where a lot of this discussion is going. And in fact, that's really, I think, the latest drivers are really talking about what's called fence-to-fence energy security. So getting away from just a few clusters of buildings that are backed up, and just kind of going all the way and saying, what's it going to take to back up the entire installation? Because it's not cheap initially, but it does, in a lot of cases, solve some more problems, and in some cases even more economically. So that kind of launches into the discussion of distributed generation and microgrids, which, as I said, is sort of the end goal in this, and the reason, one of the ultimate solutions to getting energy security at our installations. It's worth spending just a quick minute describing what distributed generation is. It's a fairly simple concept, but I've never seen it graphically displayed better than in the examples of I've seen from Denmark. This particular graphic has been around for a while, but Denmark really ran with the idea of combined heat and power, and then subsequently really got on the wind train in the last few decades. But what we in the U.S. typically have, sort of a centralized production scheme, is what you see here on the left. So you've got your big giant power stations kind of distributed around the country, and then they feed out into transmission lines and then go down to substations and distribution networks. So that was Denmark in 1985, and here's a decentralized or distributed generation model. So you can see they're a little smaller, but I suspect they're still pretty much the same plants. They still got a few big plants, but they've really hit wind in a big way, and they've got combined heat and power. That's CHP. So they're making power locally, and they're using the waste heat to heat their buildings. They certainly have nearly a year-round heating load in Denmark. So as a result of doing that, they get much higher overall efficiencies than they would if they just stuck to this big generation model, where they may have really efficient big turbines here in these power plants, but when you gotta push those electrons hundreds of miles, you lose that efficiency. So the distributed generation model, you get security because you're generating your power nearby, ideally on site. You've got on-site generation, so if the grid does go down, you've got the ability to generate your power on site, which is the end goal. And so you're less affected by outages to the larger utility grid. It's also less efficient, as I said, that example about less line loss. Typically 5 to 10% of power can be lost just moving it from the power station to where it's used. So even if you've got a very efficient power station, you're losing a lot of energy right there. And even the most efficient power station, there's significant losses in heat that don't get recovered. So if you can use the combined heat and power approach, you can collect that heat, and your overall efficiency is much higher, typically over 60% overall in terms of fuel in to useful energy out. And the distributed generation approach, this isn't a guarantee, but it generally, once you've got the controls in place to accommodate multiple generation sources, that enables it makes integrating renewable energy a little bit easier. Not a guarantee, but it generally does, because you've got a more sophisticated control system. So this is a distributed generation model. This is a microgrid right here. So this is what everybody's talking about. I'm sure a lot of folks have seen this, but so here's a utility grid coming in. Generally, all of this would be operating in parallel with the utility grid. So we would use a lot of these, say, electrons from renewable energy on our base or city or wherever. We may also be running a few generating assets here in a power plant to use the heat to heat facilities. But what's most important is we have the ability to completely island ourselves. If we lose grid power, if this substation were to blow up for whatever reason, we would be able to maintain operations inside of our microgrid. That's really all it's about. And then the most important thing in doing this are the controls in doing that. Everything has to be synced up because you've got your own grid. So it's not just one generator serving one building. All your generating assets, including your battery output, your storage output, your PV, your wind, everything has to be synced up, same frequency, same voltage, in order to make that happen. This slide, I probably could have put this slide anywhere in this presentation, but I just think it's vitally important. It's and it's also exciting, at least to me, a dorky engineer, just in terms of what is going on in terms of distributed energy and renewable energy. You know, I had this icon or this graphic up about the 4 key components to energy security. Well, 3 of these 4 components are changing really quickly. On the generation side, we've got you know, huge reductions in the cost of wind and really astounding reductions in the cost of PV or photovoltaics. This is solar panels. 75% reduction in 7 years for solar panels, and I've seen that firsthand. I was dumb enough or smart enough, whichever, to put solar on my house in 2010, and it really is about a third of the cost as it was back then. I don't regret it just because I like having it, but it's pretty amazing, and it's opening up a lot of doors into a lot of different techniques, especially when combined with battery storage. Again, that's also just really coming down, 77% reduction in just 6 years. Reportedly, we're getting to below $200 a kilowatt hour of storage. So while batteries might still be a little expensive today, and there are a variety of technologies, we need to plan for what that's going to look like in even 2 or 3 years, because when storage gets to a certain point, and you know, if all of this keeps falling, it's really going to change the landscape. And you have to stay flexible. It makes it difficult for planning these big projects. I understand that. So you do need to, when you do these security assessments and start developing these big projects, you need to put sensitivity analyses in place to figure out when there are tipping points. The inverter, the last point, inverters, that's essentially controls. The inverters are the devices that make the DC energy from solar or batteries converted into AC, which is what most buildings use. They do a lot more than that. They're pretty amazing devices, and so once you have all the electronic components of inverters, it makes it a lot easier to begin implementing this microgrid approach, so long as they're robust enough to be able to communicate with these other inverters and other control devices. So can't spend as much time as I'd like to getting into the nitty-gritty of the kinds of analyses that need to be done on this. But when we start looking at distributed generation approaches, again, I guess the points that I'd like to drive home are, after you consider your assets, generating assets, but you also consider your profiles. And it's, again, now when we're talking about a multi-building approach, it's not just one building. You look at the profiles of all of your buildings together, and in some cases they're complementary. In other words, you may have more of a load in some facilities in the morning and the afternoon, whereas another facility might have light loading in the morning, but a lot in the middle of the day. But you develop a profile overall, and then you just kind of consider the best mix of generating and storage assets to meet that profile. this is kind of getting into the nitty-gritty of what renewables do to you, do for you. But it really becomes an exercise of coming up with the best overall project. And again, when you're in this nitty-gritty stage, which it allows you to come up with the best project. All of this stuff is going to be expensive, but you can end up with some pretty impressive returns on investment, especially if you're honest and account for the operations and maintenance costs savings. So I'm going to just two other quick areas to hit on, and then we'll wrap it up and have some time for questions. But one of the big questions around this whole issue is that, how the heck do we pay for this? There's no way that we can afford to go out right away and give every military installation and every federal installation a big old microgrid. And that's certainly true, but there may be more ways to do it than are initially obvious. So again, energy efficiency. We've certainly got room for improvement. Even here, the DoD has gotten a lot better, but in terms of the types of buildings that they've got, there's room for improvement, even based on compared to just standard commercial real estate. So there's money. Again, I know it's difficult to reallocate money in the federal world, so I'm not trying to say any of this is easy, but on a sheer dollar basis, there's a lot of money that's already being spent on energy security, on energy. Some of that money could be diverted to efficiency measures, and that would free up additional money for energy security, and they go hand in hand. A lot of the energy security stuff that I've been talking about will reduce energy and improve efficiency. Other avenues, consolidation of generation. I've been on a whole lot of military bases in my career, and as you would expect, any base that has a mission function, typically there's a diesel generator lumbering behind it. They're often oversized relative to the load they serve, and especially if there's a redundant generator, which is what you'd really want, because you can never be sure any rotating piece of machinery is going to operate when you need it to. So typically you'd have two generators at least behind a critical facility. When you aggregate all of those generators at an installation together, oftentimes you'll find that you're getting pretty close to the total capacity or the total need that you would need to, you could almost run the whole base. Doesn't mean it's easy to sync all of those up. They would need to communicate somehow, but there may be opportunities, especially if you had buildings that were relatively close together, that maybe they had new generators. You could begin by picking key facilities and working to sync those up. And what you'd end up with then is you'd end up more than likely with a higher level of redundancy and higher energy security. So by doing, figuring out what you've got, it may begin to uncover some opportunities with existing generating assets. Maintenance. Comparing to the business as usual approach, and assuming, this is a big assumption, and assuming that maintenance is getting done the way that it should, because often it's not. But it costs a good bit of money to maintain a diesel genset. Fuel alone, the fuel polishing that we talked about is pretty important. The generators have to be exercised periodically, and there's just general day-to-day maintenance. By consolidating the maintenance activities, so long as you're accurately accounting for them, you can generally pick up. Sometimes you can make projects that might not otherwise seem financially attractive. You can tip the balance by by showing the savings in maintenance. Maintenance is still expensive. It's not like anything we're talking about here is going to zero out maintenance, because it absolutely won't. In fact, I'll just throw it out there that if you've got an installation you're trying to improve the energy security of, and maintenance has not been done, then well, maybe maintenance might even go up, because you're going from not doing maintenance to doing proper maintenance. But it's still far and away the right thing to do. And then finally, third-party finance. This is what almost always gets brought up when we're talking about these big marquee projects, central utility plants, and it's understandable, because it's sometimes difficult to get, or often difficult to get, the big sums of money required. There's absolutely a place for third-party financing. There's been some great success stories in all of this, but examples would be energy savings performance contracts, utility energy savings contracts, which are very similar, but are led by a utility that's serving an installation, and then utility privatization. And so that might be the case as shown in this particular slide, where the distribution on a particular base was turned over to a private contractor, and they were able to get the power underground and improve overall distribution. But there are some other models that would go along this line, where we're talking about utilities as a service. So you would have a sort of a central plant model, and not only would the base pay for electricity, but they could also produce chilled water and heating water, and so it just becomes utilities as a service. So there are a lot of different models. Again, it's all complicated. I'm not trying to say it's otherwise, but this whole world is complicated, and if you start thinking about what you can do and begin the planning early, and you can create a roadmap, you can do a lot, and you can accomplish a lot. So I'll end up just very quickly with a couple case studies, because we're pretty much out of time. I want to leave some time for questions, but these might be at least one of these might be a plant that a lot of you could visit. This first one is in the DC area. It's the Food and Drug Administration's campus just north of Washington, D.C., and it's about as clear of an example of a large microgrid as you're going to see. It serves several million square feet of lab-type spaces, very critical, and it was done as an energy security project initially. Ultimately, it was delivered as an energy savings performance contract, but initially it started out as energy security, because they couldn't afford the disruption to the scientific activities they had at this particular site. But it does produce 29 megawatts, or this is the generating capacity. It had turbines, combustion turbines, chilled water, hot water, recovered energy to make steam and hot water. And it is totally synced up with the electric utility, but it can disconnect, can and does frequently disconnect whenever bad weather approaches, or they're just not happy with the quality of the power from the utility. This has been a successful project. The local utility likes it, because they can, shed the load. And it's resulted in huge savings, largely because of that, because they get a great rate from the utility. So as I said, we do a fair bit of work overseas, and power infrastructure is really limited. So I think we're going to see kind of explosive growth, not across the board in overseas markets, where they might actually leapfrog, because there is no larger grid in place. This is an example of a U.S. Embassy compound, where at the time there was absolutely no grid. The grid wasn't functioning due to civil wars. I think it's gotten better now, but so this was pretty much an off-grid application. This was a complete microgrid. We had several buildings. We did have a diesel generator plant that was all tied together to form a microgrid. We integrated it with extensive solar PV, so that took load off the generator and saved a considerable amount of fuel. And we used the waste heat from the generators to drive a cooling process, which further helped with efficiency. So that was just a real quick rundown of a couple of microgrid projects, and I think I better turn it over to Chris and see if we've got some questions now.
All right. Thanks, Rob. Great job. It's really fascinating stuff. Now, I don't see any questions in the Q&A box here. It says there's 3. I can't see any up here. I don't know if, Nicole, you can see them. Yep, no, I don't see any here. We've got a few other questions prepared that we can talk about here. We have one for you, Rob. When running on generators only, how do you make sure you maximize PV output while at the same time preventing the generators from wet stacking?
Yeah, so that's a real concern, especially with smaller microgrids, and actually it's becoming more of a concern as photovoltaics are getting cheaper and cheaper. It's getting easier to make bigger arrays. When you're paralleling the two, there's a certain sort of lower limit to how a generator can run before it gets really unhappy. The efficiency drops off, and then you can get some condensation and some fuel in the exhaust, and it can really shorten the life of a generator. So you need the controls to really set the minimum for the generators, and typically you'll always want 2 generators if you're completely off grid, because if one generator dies, you need to be able to make sure there's another generator that can ramp up and take the load. So you need to set a bottom threshold. We've heard various lower limits from generator manufacturers, but you set a bottom threshold, and then you use your controls from your either your PV inverters themselves or some sort of inline controller to basically you have to start curtailing the output of your PV array, provided, assuming you can't just dump that onto the grid.
All right, great. There's another one from one of the audience members. What's the reason for increased number of outages the past few years?
So, just a variety. I think the biggest of the increase in outages is weather related. For a variety of reasons, maybe the distribution lines. Well, there certainly are, as that one slide shows, more extreme weather events, but the combination of even if the weather stayed exactly as it had been, as our infrastructure kind of crumbles, more stuff is going to break. So it's sort of a bad combination if you think the weather's getting a little worse, or even the weather stays the same, but the infrastructure stuff starts breaking. And then we've different areas may have increased demand. Overall, we've kind of flattened, I think, and maybe even going down a little bit in our electrical demand, but at a local level, you can get situations where a certain area becomes, a lot of people move there, or a new industry moves there, and it could overtax the local distribution.
Yeah, definitely. I know they've seen that in parts of Hawaii, California, Florida, a lot of issues like that. We have another question. It looks like somebody from one of the reserves. What are the best applications / strategies for readiness centers or reserve centers that are separate from major installations?
In terms of energy security, I would say pretty much the same strategy that I outlined, where it's going to be hard today, and again, this could be changing. It's going to be hard today, I think, to get away from standard diesel genset as sort of your workhorse, or maybe your base load for backup generator. Now that's changing and there's absolutely some exceptions, but you know, you sort of treat that as step one, and then augment with PV in some way to control the PV. It's a pretty cost-effective way to do it. So the PV gives you benefits year-round. Almost most areas will allow what's called net metering. So any excess the PV does just goes onto the grid in normal case, and then if you lose grid power, then you just have the controls that we talked about for syncing up the PV production and the generators.
Yeah, that's excellent. And I know there's some opportunities depending on the states that you're in, where you can get funding from the state, and the reserves are often half funded by state, half by federal, or some mix. So I know California, Connecticut, Massachusetts, and New York, and Maryland actually have funding available for microgrid development strategies, so on, a lot of CHP focused as well as solar. So that might be helpful as well.
Yeah, great point.
We have another question here. So can centralized generating plants be used for emergency power and legally required standby generators as defined by the NEC, National Electric Code?
It's possible. It can. There's just a lot of considerations that you need to take into account. The biggest being that they'll need dedicated feeds. So you wouldn't necessarily be able to rely on the distribution coming from your central generating plant. You may well have to do sort of another ring that's an emergency power ring that everything else can be shed from. That's just emergency power that serves your emergency loads. Now that said, and that could be expensive certainly. That said, it's something you would always want to coordinate closely with the utility and then your base personnel, because they would be the authority having jurisdiction. So there may be some special cases you could do depending on the proximity and what you've got going on. But generally, you would need separate feeds.
All right, great. So we still got a few minutes left. We have a few other questions if everyone's interested. One of the things that you noted is that advanced microgrids with renewables and CHP offer the greatest benefits. These complex projects can require long planning timeframes and potentially more than one procurement method. And you mentioned a few of them. For example, both a power purchase agreement and an energy savings performance contract might be needed, or other mixtures of complementary procurement vehicles like those. What kind of strategies might you recommend for facility managers starting to plan microgrid development?
So, yeah, I think the best would be to start with the energy security assessment, and a healthy component of that would just be kind of figuring out what you've got and where you want to end up. If you're going to be looking at combined heat and power, which you should, if you think your installation might be right for that, then you need to kind of keep that in mind as you're developing new buildings. We see, sometimes, again, I'm a mechanical engineer, but we see sort of new buildings getting constructed, and they'll have kind of a completely different mix of systems that make it difficult to later integrate other systems. And I'm talking, let's say, specifically about steam or something like that. You need steam at this facility. It's like, why would you put a new building in that needs steam? Is just an example. So you need to kind of keep your eye on where you want to go, and then start to think as an interim step what you can do to combine facilities. You may have two critical facilities right next to each other. Well, that's sort of a foothold you can do to try to make a bigger project. But there's no getting around it. It's complicated, but you're already spending a boatload of money, so you just need to just kind of get yourself a roadmap.
Yeah, that's great. And having a roadmap is really the best way to get through some of these more complicated strategies that are involved. We did have a question about getting access to this presentation, and I believe we said earlier that it will be available afterwards. You'll be asked to go do a survey, and I believe once the survey is done, here it is, and that's going to be made available to everybody. And I think that Nicole said if you really want to have it as well, you can email her, whose email address is on the beginning of the presentation, or the invite for the presentation. Let's see, we got still a few more minutes. I have another question here. So energy storage is often cited as vital for energy assurance and microgrids, as you mentioned. Yet batteries remain very expensive in most applications and locations, although prices are falling, as you did note. How do you view the role of energy storage in energy assurance, and what would be needed to increase deployment of batteries and the other energy storage technologies?
Yeah, so so fuel, again, is the most common energy storage means, but batteries are pretty exciting. In terms of their continued rollout, you know, I think the only thing in their way now is just getting the price down, and hopefully, you know, we don't see too many catastrophic events. You know, there probably will be fires in other electric cars, you know, which are the biggest, or some of the biggest users in batteries. But I think I think we're just going to see more and more of them, and they'll start, you know, with smaller systems, maybe life safety systems. We're only talking, you know, a few tens of kilowatt hours, but we'll see their continued rollout. I'm a mechanical guy. I love pumps and fans and rotating stuff, but there's always something. There's something about no moving parts that I think is always going to win the day. So I wouldn't totally bet against batteries. So yeah.
Yeah, we see that as a big opportunity. I went to a summit last week all about solar plus battery storage as really going to the next level here in the next few years. And, you know, there's another great question here about the role of utilities, right? And that came up a lot in this battery storage summit. And what do you think would be the best roles for electric utilities to support energy assurance and microgrid development? Do you see different roles for vertically integrated utilities compared to electric distribution companies in restructured states that no longer own generation?
Oh, boy. I'm not sure I would advocate sort of going back to the one vertical integration model, but I would say that utilities, I think, just from my perspective, I think they need to be a part of it, and I think there's huge opportunity for them as well. You know, this is just me privately saying, I think, you know, they're looking about, you know, there may be a little bit of turf considerations from some utilities, but I think if they get on board with the big renewables and you know, at least some storage to manage the rapidly changing demand, I think they're going to be the big winners in this because they've got the purchasing power. So I would hope that they start to see that, and I think some are.
Some are, and I think, like you had mentioned earlier, in some of the states where they're seeing a lot of growth in their grid, this is turning out to be a great opportunity for them, where they don't have to put in peaking plants as much. If they can rely on demand response and battery storage and solar and integrating them all into their grid, it can really make a huge difference, and not having to buy that expensive peak power, you know, with like oil-fired generators and that kind of stuff. So I think we probably have time for one more question. So one of the things I hear about microgrids a lot is, you know, this is all very complex stuff and it's custom solutions. And do you think there are certain things that can be done to make microgrids more sort of plug and play, more standardized, scalable, and maybe even modular? Or are custom solutions likely to dominate this energy assurance solutions for some time to come?
Yeah, I think, to a degree, there's always going to be a certain amount of integration that's required, system integrator, and it'll be there will be some customization, but I've been struck by just the sheer amount that the controls have changed. Again, I brought up that case of the inverters, that there's so much going on inside of these inverters that not to minimize what has to go on in generator paralleling and generation paralleling, but the electronics have gotten so much better that I think I kind of feel like in some respects we're almost there in terms of plug and play. It's by no means plug and play yet, but the components seem to be talking much better to one another, and they're just the fact that everybody seems to be offering microgrid controllers now kind of says that the industry has kind of figured it out, and it is complex. Absolutely, I'm not minimizing that, but it's not like it was even 10 years ago, where it was an extremely exotic and difficult thing to do. That's just my opinion. So.
All right. Well, that's great. We certainly are starting to see some of the same thing in both the federal markets and state and local government markets, because it's difficult to create something that's customized over and over and over again and really get it to scale,
Right.
So, all right, I think we're closing in on the end here. We want to be able to finish right on time and be respectful of everyone's time, which is at a premium these days. I want to extend a warm thank you to our speaker, Rob. You did a fantastic job. All of our attendees, thank you all for taking 90 minutes out of your busy, busy days. On behalf of the Society of American Military Engineers and TME Presents, we appreciate everyone's participation. I hope this webinar has been useful. If you have any additional questions, please submit them via email to Nicole Matthews at nmatthews, that's MATHEWS, at SAME.org. This concludes the webinar. You may now disconnect and have a wonderful day. Thank you. Take care. Bye-bye.
Thanks, everyone.